Hi everyone, and welcome to another episode of Space Science with Python. Or today it's just Space Science without Python because I would like to talk a little bit about this apparent magnitude topic we started last time. So last time you see here the Jupyter notebook we created where we defined this so-called HG function to compute the apparent magnitude. Just a reminder, apparent magnitude means the brightness of an object, especially of asteroids and meteoroids. And smaller apparent magnitudes corresponds to a brighter object. So this is just a quick recap. And we defined this function here in this cell with a lot of documentation and stuff. And it's basically this function here, the HG function, where we computed the apparent magnitude for the object 433 Eros. So if you don't know how to compute it and so on, just go back one video before and we go through the cells here step by step, and I explain to you how to compute the apparent magnitude of this particular object here now next year, where it has an apparent magnitude of around 12 or 11.7 Mach. So today we will talk about something that is quite, let's say unique for this apparent magnitude function. It's called, as the title suggests of the video, the so-called opposition effect. And the opposition effect, it is, let's say, encoded in this function and also its sub-functions. Yeah, so it's quite hidden somewhere here, but you really don't see it now because there are a lot of variables and so on. It's quite difficult to imagine. Of course, we could simply use Python to draw the function, the apparent magnitude based on the phase angle, the distances, the size of the object, and so on. But my suggestion today would be, let's go first a step back, talk about a little bit qualitatively. So what do we expect from this function? And then next time we will use Python to really get a better understanding on a quantitative way. So the opposition effect is something that you may have heard or not. Let's take a quick look at the picture taken by Buzz Aldrin on the moon's surface. So you see here the moon's surface, you see here the shadow of Buzz Aldrin taking a picture of the surface. And what you may see is, it's a lot of gravel and stones, boulders, whatsoever. And a very quite uniform distributed brightness. So the sun is in his back, you see his shadow, and it looks quite fair. But you see here around his head some kind of, brightness or illumination increase. So it's a little bit brighter than the surroundings. So is this an error or a camera bug or whatsoever? Well, no, this is the so-called opposition effect. And before we dive deeper into it, you can, or explain it, you can actually reproduce this thing on Earth. So what you need to do is you go to the beach, for example, or a meadow or whatsoever, some plain ground. Especially it would be nice if it would be like gravels or sand or something. And you take a picture where the sun is in your back and you make a picture of your shadow, and you will notice something similar. You will notice this quite illumination increase around your head or your body or your camera. So just take a look at this, try it out, and you will see this so-called opposition effect. And we will also talk why this opposition effect occurs and why it is important to know, because it's also quite important for our NEO project and the understanding how we can observe or discover objects as, let's say, efficiently as possible. Now, first of all, I would suggest let's go to our planetarium software, Stellarium. And here I would like to, to show a little bit how the magnitude varies for a particular object. So before we start, I would suggest to remove the ground, the atmosphere, and also the cardinal points. We show the equatorial grid, and we switch to the equatorial mount. So we move our telescope with this grid here. Now let's search for a particular object. I would suggest to take Ceres, and we see Ceres is currently here, very close to the sun. So it's also now a new moon. So the moon is here. You see also Venus a little bit here next to the sun. It's quite close, so you won't really observe it. It says a magnitude of 8, but I think it's virtually unobservable because it's so close to the sun. Another value next to the magnitude is something here. You see here the phase angle is currently 7 degrees. Yeah, so what is the phase angle? A small recap. Let's switch here. We have here our sun in the center. We have our planet Earth somewhere here, for example, and then let's draw a gray thing that represents our asteroid or any O. So let's say in this case we draw a series, which is maybe somewhere here. And now we can draw some lines. We can take from series a vector to the sun, so here, and we draw another vector to Earth, which is here. So of course we have here the distance between the Earth and Ceres, and we have also here the distance between the Sun and Ceres. Yeah, so just write me an index or something. It's not really important though. And the phase angle is the angle that is now enclosed by these two vectors. So let's say the phase angle phi. And as you may see, well, the angle varies a little bit if we have geometry that is like here. So now it's like, I don't know, let's say 7 degrees or so. This is now the current state. But yeah, if we, over the time, we revolve around the sun and Ceres revolves around the sun, but we are a little bit, let's say, faster. So at some point, let's remove everything. At some point, Earth will move. Yeah, let's say we are at some point maybe here. And Ceres will also be somewhere, maybe here. And in this geometry, we have, well, again, our vector from Ceres to Earth and from Ceres to the Sun. Yeah, let's say they are almost identical. And now this angle here is, let's say, almost 0 degrees. And this is called the so-called opposition. Yeah, and you may see, okay, opposition effect, it's somehow linked to this geometry. And we will talk about this just in a moment, but let's have a look how the brightness of Ceres behaves over time. So we have now here 8.7 meg. Just take a look here also at the phase angle. And let's let's go a little bit forward in time. So we see here the phase angle is now 13 degrees, 18, 21, 19, 10. And now we see it's decreasing. So we are maybe close to the opposition. It won't reach 0 degrees, of course, depends on the orbits, but we have now here 6 degrees and now we have 7 magnitudes. So you see here the end of March. Now let's go a few days further. You see after a week or so, we still have 7 mags around. But if we just increase now the time a little bit more, you see how the brightness goes down quite rapidly. So now half a magnitude after a month. And then, yeah, more and more over time. The same goes also applies for the same into the other direction. So around the position, the magnitude or the brightness appears to be, let's say, stable, and afterwards it decreases quite rapidly. And this is the so-called opposition effect. So if we draw, we'll do this with Python, so you will see it's actually really an actual legit effect. We will draw something like the magnitude, so the brightness here, over, let's say, yeah, the phase angle. Yeah, so we can here say this is 0 degrees, and here we have, like, I don't know, let's say 30 degrees or so. You could also go into the other direction, it's symmetric, but yeah, I don't mind now. And let's take something for the brightness, like yellow. You will see that the brightness increases quite rapidly to a phase angle of around 0 degrees. Yeah, okay, it's not really a singularity, of course. It will reach a maximum. It will look something like this, maybe. So this effect here is the so-called opposition effect. So this brightness, this increased brightness at around 0 degrees phase angle. What you will also see when you take a picture, because it's basically the same geometry, right? Because you have the sun in your bag. So we can draw here again our sun with the rays. You have here yourself making a picture. on the surface of our Earth. Okay, you're not floating, but you get the point. You're taking a picture into this direction here. So this is the field of view, let's say. Here you have some, I don't know, sand or so, and you will see that the phase angle here is also, yeah, it's almost a straight line, so it's also 0 degrees. So this is also the opposition geometry. So surface, observer, and the illumination source, in our case, the sun. Now, why? Why do these things happen? And there are two major effects that are responsible for this. The one is a little bit more a geometric effect, and the other one is more a quantum mechanical effect. I would suggest let's start with the difficult topic, with the quantum effect. We will not dive too much into detail, but there is one thing called coherent backscattering. And, well, let me just draw some small pebbles or gravel or very, very small grains of sand, for example. And these grains here, they have the size and also the distance between the grains is very close to the wavelength of the light. And this enables the light, or let's say it gives the light a certain, I wouldn't say advantage, but like a property that when the light is coming in from this particular direction, it will of course scatter around, right? It will reflect here and there and so on. And it will go, of course, go in any direction, right? But there is a certain preferred way, namely the way it came from. And this leads to an increased illumination if you are, for example, also standing here and observing it, right? You take a look here and you see that it's getting way brighter at a phase angle of 0 degrees compared to larger angles. Of course, there is light and so on, but especially the 0 degree angle is quite high. And this is called coherent backscattering. So just take a look at this. It's really interesting because it is an effect you see really in your daily life if you take a look at this, and also in space science with our asteroids and so on. So this is the one effect, the coherent backscattering, based on this scattering on the small grains in the material. And the other effect is so-called self-shadowing. And the self-shadowing is also quite important, especially for certain surfaces, rough surfaces, and so on. So I would suggest let's draw first a small surface, but with a way smaller scale than we see it, because the surface appears smooth and so on. But of course, the surface is not smooth. We have a lot of different stuff in there. So for example, we have, I don't know, we have small stones, pebbles, gravel, whatsoever. We have maybe, here's a spike, I don't know. So you get the idea, right? There are a lot of different shapes here. It is really very diverse surface that has a lot of different shapes everywhere. And if we have now our sun, for example, shining from a certain angle, so let's say from the left, what happens is we have something called self-shadowing. So self-shadowing is something you also have heard or seen. For example, if you take a selfie, shadowing. So if the source, the illumination source, is just from a different angle, not from on your front face, of course your nose will create a shadow on your face, or even other parts of your body, of your face, will create small shadows all over the face. And you know, also depending where the light's coming from, the mood is appears to be different. But yeah, these are some psychological effects. But basically, you cast shadows on yourself. This is self-shadowing. And the same thing applies here as well. So we have here, let me draw the shadows now in red. We have, of course, here also shadows. So for example, we have here a shadow. This one casts a shadow here. This one casts a shadow. Here a shadow is casted. Here as well. We have here a huge shadow all over in this area. So The areas that are illuminated are at the end of the day, yeah, like here this area, and here this area here, and so on. Now, if the sun moves now a little bit, so the radiation source goes from the top to the zenith, and we are standing also in the zenith, so in the top, yeah. So the observer, we are here again, looking downwards, and also the sun is shining down. So let me just draw it here. Then, so these are the rays, the sunlight. Then, of course, this red shadow, or the shadow effects, will disappear. They will vanish. So we do not have any. Okay, I just removed the stone, but yeah, doesn't mind now. This self-shadowing will vanish quite rapidly, especially for very small angles, so close to the opposition, right? So a position effect to 0 degrees, a phase angle of 0 degrees. So the self-shadowing almost, yeah, let's say disappears, and the illumination surface is now not only these small parts here, but really the entire surface, and of course the upper parts of this pebbles, gravels, and so on. So there's no shadow being casted. Of course, minor shadows are always somewhere, but we have here a way larger illumination surface, and this effect increases rapidly for very, very small phase angles. So if you see it in the opposition, especially in the opposition, you then see this opposition effect. So this is the second effect that causes this effect here you see on the picture from Buzz Aldrin. And this effect is also important for discovering near-Earth objects and asteroids, because if you know this opposition effect exists, and you know the time frame is maybe small, and there's only a particular region in the night sky where these objects are in opposition, then, well, there could be preferred regions in the night sky where we observe NEOs. And this is something we will answer in the next videos. So in the next video, we will take a quantitative look at the functions and see this opposition effect really in our Python functions. You can play around already now if you like, but this video here gives us a little bit explanation of something that, let's say, will happen in the future videos. So I hope you learned something about the opposition effect, also called opposition surge. So if you want to take a look at, for example, Wikipedia, and it's based on two major effects. The one is the coherent backscattering, and the other one is the self-shadowing. So take a look at this, and I hope you're looking forward for the next video, and then we will go back into our coding part with Python. And until then, I wish you a nice week. Take care and see you next time.